Great, thank you. And for the last talk of the section, we have Ed Borasky with Microtonal Algorithmic Composition with R.
Okay,
That'll be this.
it's me. Okay, well, all I need is the right arrow and the microphone. Which one is which? This is the microphone. This is the right arrow. Okay, got it. Yeah, I'm just going to buzz through this. Like his presentation, my stuff's all online. I'll post a link in the Slack and everything. So you hear me? Okay, one, algorithmic composition. There's a great book with an overview of all the methods, Nearhouse 2009. Again, the references are all at the end of this. You can download it. There's Markov models, stochastic, generative grammars, transition networks, chaos and self-similarity, genetic algorithms, cellular automata, and artificial neural networks. My main compositional focus is on the Markov models and stochastic. This was pioneered by Yanis Xenakis, who passed away in 2001. What I do is random chord projections on microtonal harmonic structures. That's a $10 word for like random, not like throw dice and read the dice and pick stuff up. My one published piece is up on Bandcamp, and that's the microtonal harmonic structure is Harry Parch's tonality diamond, and the tonality diamond was an inspiration for Erv Wilson's combination product sets, which is what I'm going to talk about later. Strange historical note, I was actually exposed to Harry Parch's music and microtonal and algorithmic composition as an undergrad. So I went straight from marching band to microtonal algorithmic composition. Anyway, the types of scales, the standard Western tuning that we all know and love, except for the people like me who hate it, is 12 equally spaced tones per octave. It's abbreviated 12 TET, which is 12 tone equal temperament, or 12 equal EDO, which is 12 equal divisions of the octave. I prefer the second form, and I'll explain why in a little bit. Alternative tuning is everything else. So here's what the first object that comes out of the package. This is the 12 TET equal scale table. Now, the leftmost column is the note name. If you know anything about music, you'll recognize those note names. The ratio column, that's the numerical ratio of the row to row one. Row one is the root unity 1-1 in just intonation terms, and the ratio frac that's an interesting column. There's two types of scales. There's scales that are defined by irrational numbers, and there's scales that are defined by rational numbers. Since this particular function doesn't know which one, it just has a routine to convert back and forth. There's an R package called fractional that does that. And these are irrational ones. So what's in the ratio frac column is the best approximation the fractional package could give. A ratio sense, that's another, I've got a slide on that coming up next. But that's the value, the ratio of that note to the root in sense. And then the interval sense is the difference between the sense, the sense on the left, is there a pointer? Yeah, between this number and this number. And you can see it's all 100 here. And then the degree is just the degree of the note. They go from 0 to however many notes there are minus 1. So actually it's degree 0 through degree 11 is the scale. And then it repeats at a ratio of 2, which is an octave. And that is the period of the scale. Now, an alternative tuning, you can change all of this stuff. Okay, cents are, it's a logarithmic measure used by scale theorists. 1 cent is 1/100th of a semitone. So 12 semitones is 1,200 cents. It's 1 octave. It's a ratio of 2 to 1. So that if you go back to this table, you can see the cents are all 100 because the ratio is a 12th root of 2 between notes, which is the log. Now, alternative tunings, this is where it gets interesting. Scales from other cultures, the most common ones you'll run into are the gamelan scales of Indonesia. I forget what the scales for South Indian music are called. Makam scales from the Turkish Arabic world. And then just scales. These are scales based on rational numbers. There's a long and ugly history as to why we don't use just scales and we use the equal tempered scale. Now, the scale repetition period is different from the octave. There are a couple of fairly well-known scales that use a period of 3 instead of 2. So it's a perfect 12th, and it's divided into 13 equal tempered scales. That's one that's very common. And the scale repetition period divided into more than 12 tones. And combinations of the above, that's where it gets really interesting, because there's an infinite number of possible scales. So microtonal music, technically speaking, is usually defined as an octave divided into more than 12 tones. So the most common examples of that are 19 TET, so you divide the octave into 19 equal tempered divisions. 24 TET, aka quarter notes, and quarter tones, that'd be 50 cents each. So really they should call them, the quarter tones should be 25 cents each, right? And 31 TET. Oh, okay, now we get to Erv Wilson. This is the interesting stuff. He's a Mexican-American prolific music theorist. He spent almost his entire life developing these theories. He developed keyboard layouts, he developed scales and algorithms for generating scales and lattices for explaining how the notes in the scales related to each other. And he's primarily known for his theories of microtonal just scales. Now we get into the math here, combination product set scales. That's the focus of this package. We start with a set of n harmonic factors. And for an even number of factors, we choose n over 2 of those factors. And you'll see an illustration of that coming up. For an odd number, you have your choice of either n over 2 minus a half or n over 2 plus a half. So if you have 4 factors, sorry, Dean Oliver, this isn't for you. Nobody gets that. It's a basketball joke. For 4 factors, you choose 2. There's 6 combinations. That's called a hexany. So it's hex is like the Greek word for 6. If you have 5 factors, you choose either 2 or 3. And either way, it works out to be 10 combinations, which is called a decany. And if you have 6 factors, you choose 3. So that's 20 combinations, and that's the Eikosany. Pascal's triangle is your friend when you're dealing. It's really interesting if you go through the Erv Wilson's work. He actually discovered a lot of mathematical things like Pascal triangle in the course of building these scales. So we're going to make a hexany here. So we take all of the combinations of the factors with choose elements. We take the products of the combinations, reduce the products to ratios in greater than or equal to 1 and less than 2. Divide by the smallest product. multiplier divide by powers of 2 to get values in the half open interval 1, 2, and then you sort them. So we'll work through that. Here's the example, the 1, 3, 5, 7 hexany. The 1, 3, 5, and 7 are the harmonic factors. Good, I'll make it. Product of the combinations are 1, 3, 1, 5, 1 times 7, 3 times 5, 3 times 7, and 5 times 7. The raw ratios, we divide by the smallest product. So the first one's 1, then 5 over 3, then 7 over 3, then 5, and then 7, and whoa, 35 over 3. They reduce that to the period, reduce that to within the octave. So to be 1, 5/3, 7/6, 5/4, 7/4, 35, 24. I did all of these in my head. So the question is whether they're right or not. And we sort them. So 1, 7, 6. The sorting I didn't do by my head. I used R for that. But the sort is 1, 7, 6, 5, 4, 35, 24, 5, 3, and 7, 4. Now let's ask the R package what they are. And there they are. I don't need to blow this up, do I? This first column there is the note name, and it's 1 times 3, 1 times 7, 3 times 5, 5 times 7, 1 times 5, 3 times 7, and 1 times 3 prime. The prime indicates it's the next octave up. And see, there's the ratio. And these are the numeric ratios. You see now the fractional ratios are just what I had on the previous slide. You can go back and check that. The ratios in cents here, they're not 100 anymore. They're bigger than 100 because there's only 6 notes to the octave. If there were more than 6 notes to the octave, most of these ratios would be less than 100. And then the intervals between the notes are also, they're not the same. It's not equally tempered. It's just. And this is the last piece here, the chord table. Like the scales, the chords are a combination of harmonic factors. This is a little, this is too complicated to explain. And currently, so I just printed one out. Currently, I can tell you how many there are. It currently only works for even numbers of factors. For a chord table, you take choose plus 1 combinations. So for 4 factors, you'd have 3 combinations because you had choose was 2. So you have 3 combinations. So there's 4 triads. And for 6 factors, there's 4 combinations, 15 for tetrads. You can get these numbers off of Pascal's triangle. But there's 2 kinds of chords. There's harmonic chords and subharmonic chords. Each chord has a harmonic and a subharmonic form. Roughly corresponds to major and minor chords. They sound that way, at least for some of the microtonal scales. So 4 factors, you have 4 harmonic triads and 4 subharmonic triads. For 6 factors, you have 15 harmonic tetrads and 15 subharmonic tetrads. And in the chord table, the subharmonic ones have the slash in their names. So here they are. There's the 8. There's the hexany chord table. So in my remaining minute, I'm going to go through the road, skip up to the road map. Roadmap, current status. There's enough infrastructure to manually make music, which was my original goal for building this thing. The documentation, well, you're looking at it. There's a package down site, but I think I put a warning on the page that if you wanted to use it, call me first. Yeah. The current plan is to clean up the documentation so other people can actually use this if they want to. And I'm hoping to release a new album on Bandcamp and open feature requests for triage and such, and add a consonance analysis capability. That's really why I wanted to build this in the first place, because there's like 5,000. There's a scale archive online with like all the scales that this guy knew about. And there's like 5,700 of them. And, you know, I'm never going to hear them all unless I write a program to write one that goes like every five minutes a scale or something. And remove the MIDI functionality. That MIDI is a great language for 4/4 time equal DO, 12 DO music, not for anything else. And the other tools in the appendix are designed to deal with what MIDI deals with. So, and where does all this stuff live? I'll just leave this slide up. People want to write this stuff down or not. And I'm off.